Physics fans, Mr. Russo with AP Physics, just doing a follow-up on yesterday's acceleration, Newton's second law discussion and lab activity. So what I did was took Group 1's data. They had a 12-degree angle. I think that was 3 or 4 books. I used the class average for the kinetic friction of wood on wood blocks of 0.25. The group had 150 grams, which is roughly 1.5 newtons of applied force pulling uphill. And we massed the block at 182.8 grams, or convert that to our base units, 0.183 kilograms. Then we ran the trial several times, and in retrospect, I did a bad thing, which was I helped them scrub their data and lost a couple of heavy values because they didn't seem to line up. But in retrospect, that would have brought this average acceleration up a bit. So I'm thinking towards next time, making some adjustments to the scales in that drag race file to better capture what we're doing with this slab. I think we were asking a machine to only capture roughly a second's worth of information and extrapolating that data. And that's probably leading to these big errors that we get. Plus the conversation we had about Newton's 3 laws can't be divorced from one another. All right, so then I drew a picture. Here's our 12-degree ramp. Here's our block. I drew our weight vector. I drew our applied force vector in black pen. And then I had a conversation with myself, thinking, what are the components of force? I've got this downward component of weight, which we would call the normal force acting up, pushing the block up so that it stays still, not going through the ramp. And then I have that component of weight which tends to make you roll down a hill, right? mg sine theta. Okay? And I just put those values in, right? Since it's low angle, most of your weight is still acting with friction. All right, so then continuing our free body diagram, that means that I have 0.42 newtons of component of weight pulling me down the hill, right? That 0.42 is the missing from up here. And then I've got 0.49 newtons because the force of friction is mu f of n, right? Using that value of mu up here, this value for normal force. Then the sum of the forces is, what I'm left with is a 0.5 newtons pulling me uphill, causing the acceleration, right? These two are opposing motion up the hill, and so that's what I'm left with. Sum of the forces is mass times acceleration, is Newton's second law. So my theoretical acceleration up the ramp with that force and that mass, I should be seeing about 3.2 meters per second squared. But we saw 1.6, and again, we would have seen more had I not encouraged them to lose some data. Bad teacher. And using that, I calculate a relative error of about 50%. Not bad. Not great, but not bad. We'll see if we can do better next time. Hope that explains what we saw yesterday, and hopefully you will have some questions in class next time. Over and out. See you later.